Hello, universe. Today we'll be talking about quantum mechanics and deriving the Schrodinger equation. So in quantum mechanics, I have my system is represented by a state vector in a Hilbert space. And if I write that in the position basis, then that's going to look like a wave function, okay? And the wave function, is a function from space-time into the complex numbers, whose modulus squared is a probability distribution of finding a particle at a given location, right? So if you think about, for example, the hydrogen atom, and we're modeling the position of an electron orbiting the nucleus of a hydrogen atom, then we're going to use a wave function to do this. And again, the square of the wave function is exactly the probability distribution of finding the electron at any given location around the nucleus, okay? Now, to describe the time evolution of a wave function, or more generally of a state vector, we want to use something called a unitary operator. The reason for this is probability conservation. If I have a state vector representing a system, then I want that vector to have norm 1. And this corresponds to the fact that the wave function needs to have an L2 norm of 1. In particular, the integral of a probability distribution has to be 1. The total probability always has to sum to 1. If I flip a coin, the probability that it's heads and the probability that it's tails have to add to 1. And this is true of any probability distribution. Its integral must be 1. And so to enforce this conservation of probability mass, we actually need to require that if I apply my unitary operator to the state vector, then if I look at, the norm of that new resulting vector, it must stay 1 due to probability conservation. So if I look at what that norm is, it's just going to be the expectation value of u dagger u, where u is my unitary operator. And since I want to enforce that this expectation value, or this norm, is all identically 1, then I'm going to enforce that u dagger u is just the identity matrix, which is essentially saying that u is a unitary operator. Now, if I want u to be a time-dependent unitary operator, I'm additionally going to add the assumption on time, which is a Markov property, essentially that my family of unitary operators, okay, is going to depend on time in such a way that the time evolution of the system is forgetful, in the sense that it only cares about the present moment, doesn't care about past history. It only cares about the current state, and the exact current state at the current time will determine the time evolution of the system, okay? Now, with these two assumptions, we can basically construct the unitary time evolution operator of the system as an operator of the form e to the I h t, where h is a Hermitian operator and t is time, okay? So the reason for this is if I take the Hermitian conjugate of this operator, e to the iht, if I take its Hermitian conjugate, I get e to the minus h dagger t, but h dagger is equal to h, so I actually get e to the minus ht, and then I recover the inverse. So I basically, by taking the dagger of e to the iht, I find that its dagger is actually its inverse, okay? In particular, it's a unitary operator. Now, the fact that any unitary operator, which is sufficiently regular, can be expressed in the form e to the iht, where h is a Hermitian operator, is a result called Stone's theorem, and it can be found in Michael Talleyrand's Introduction to Quantum Field Theory textbook. Now, this is an extremely powerful and non-trivial result, which essentially makes all of physics work. But once we assume that our unitary operators are a one-parameter family in time of the form e to the iht, where h is a Hermitian operator, then we're in business. Because recall that a Hermitian operator corresponds to an observable, okay? Why? Because its eigenspectrum is real. And so if I take the state of a system and I write that state as a linear combination of the basis vectors of my Hermitian operator, then that linear combination, the coefficients of that combination, their modulus squared, is precisely the probability that the state will be observed to have an eigenvalue, to have that corresponding eigenvalue, okay? So if I expand, for instance, if I look at the Hamiltonian operator, which is an operator associated to the observable of energy, okay? The Hamiltonian operator, or the energy, will have a discrete spectrum in certain cases, like the hydrogen atom. So we'll have a discrete set of energies, a discrete set of numbers that I can observe. And if I take an arbitrary state of my system, I can write that state as a linear combination of the energy eigenvectors. They form a basis or a complete resolution of my Hilbert space. And so if I look at the coefficients of the state vector in that basis, which are precisely given by the projection of the state vector onto that eigenvector. So the magnitude squared of those coefficients are precisely the probability of observing the system to have that corresponding eigenvalue, which in this case would be a corresponding energy level, okay? So this is why we care about Hermitian operators. They correspond to observables because their eigenspectrums are real. And so what we're observing is an eigenvalue that's real with probability given by the magnitude of the projection of the state vector onto the corresponding eigenvector. Now, I've assumed that my time evolution operator for my quantum system is unitary and thus is of the form e to the I ht, where t is time and h is a Hermitian operator. So if I expand this expression for small t, for small time t, I'm going to get locally Taylor's approximation of the form identity plus IHT. Okay, so locally my time evolution operator for small times looks like 1 plus IHT, where h is a Hermitian operator, okay? And here is the crazy part, is that now if I write my differential equation, okay, so if I just look at the state vector at a time t plus dt, and I compare it to a state at time t, well, the difference is precisely applying the operator 1 plus I h dt to my state vector. If my state vector is at a time t, I simply apply the operator 1 plus I h dt to that state vector, and I get the new state vector at the incremental time t plus dt. And I can use this expression to derive a differential equation. And the differential equation is simply given by the fact that I believe it's like, yeah, it's going to be I times the time derivative of the state vector is equal to h times the time derivative of the state vector. And that you can just do by just working out the algebra, okay? So once you have this expression for an infinitesimal time evolution of your system, you can work out the algebra and solve for the time derivative of the state vector because you understand its time evolution. When you work out the expression for the time derivative, it's precisely I times the time derivative of the state vector is equal to h times the h operating on the state vector. And now what is h? Well, h is called the Hamiltonian. So h is precisely the Hamiltonian, which corresponds to the energy observable. Now, why is h the energy observable? Why does time evolution somehow relate to the application of the Hamiltonian operator? Well, this is due to a deep fact, okay? A deep fact about symmetry, in the sense that time translational symmetry represents a conservation of energy. Just how space translational symmetry represents a conservation of momentum, and rotational symmetry represents a conservation of angular momentum. This is called Noether's theorem. It's an extremely powerful theorem in physics, one of the most beautiful theorems I've ever seen. And the idea is that symmetries of our theory imply conservation laws, or symmetries of a system imply conservation of some quantity. So in this case, we've assumed a time translational symmetry. So I've assumed that the physics occurring right now and at the present time in 2024, whatever year it is going to be the same as physics being done in the year 8034. Okay, I've assumed a time translational symmetry. This is the Markov property, or the forgetfulness property that I was describing before, where the state vector is essentially only cares about the present moment and the configuration of the system at the present moment, doesn't care about the past history. This is a time translational symmetry. And when I assume this time translational symmetry, what I end up with is an energy conservation law and a time evolution which is governed precisely by the application of the Hamiltonian operator. And so you can see that the Schrodinger equation just arises from assuming that the time evolution operator has a specific form, e to the iht. Once you assume that the time evolution operator takes that form, the Schrodinger equation is you get instantly, okay? Just by unpacking the expression using the Taylor's expansion. Now, what the key, the physics here, what is the physics? Well, we're assuming a property about time. And when we assume this property about time, the time translational symmetry of our theory, this Markov property, and we assume a conservation of probability, then we end up with a time evolution which is governed by this Schrodinger equation, essentially by negative I times the Hamiltonian applied to the state of the system. So there's deep physics occurring here. And I hope you have a great rest of your night.